Hi everyone, my name is Joseph Hunsaker, and welcome to my course, Web3 Fundamentals. I am a software architect, consultant, and entrepreneur. I take coding and technology very seriously. The internet is poised for a fundamental shift, but how? It is shifting from a network of information to a network of value. Blockchain brings substance to the internet. Blockchain is to the internet as gravity is to life. This course is about a new class of technologies that will be a part of our everyday lives, offering us and our communities independence from big tech with a new breed of applications. Some of the major topics we will cover include how blockchains provide a new foundation for technology innovation, how applications are built on blockchain, an overview on game-changing decentralized applications. By the end of this course, you will have a sense for the important role that blockchain will play in shaping the future, and you'll know how to start using blockchain today. From here, you should feel comfortable diving into Web3 with courses on decentralized finance or DeFi, non-fungible tokens or NFTs, Solidity smart contracts. I hope you'll join me on this journey to learn blockchain technologies with the Web3 Fundamentals course at Pluralsight. Welcome to this course on Web3 Fundamentals. It's a privilege to be a part of your journey into the future of the internet. Web3 is still evolving and can mean a lot of different things to different people. In general, Web3 is about the decentralization of applications and platforms, empowering us, the users, to participate in the benefits of building those platforms, something a lot of us are not quite used to as a consumer, where we simply benefit from using the applications. While Web3 is not exclusively tied to blockchain, it serves as a powerful technology for Web3's foundational principles. Let's get started with the basics of blockchain. Put simply, a blockchain is a series of data blocks. Each new block is linked to the last. With a focus on data like this, we may call all of this information a database. What is a blockchain? We could say it's a database, and that would be true. But a blockchain is more than just a database. Besides data, we mentioned that each new block is linked to the last block. So how is this chaining significant? Well, one way it's significant is that it provides a sequence. One block must follow another through time. A chronology. Wow, so just by saying they're linked, we have somehow pulled time itself into the mix? A blockchain is a lot like history. Interestingly, a blockchain shares more than a surface-level comparison to history. History will serve as a great analogy to many key aspects of a blockchain. History is something we all understand after all. When we speak of history, we speak of the events of the past. An event in history is like a block on the blockchain. History unfolds with the passage of time. Blocks, through time, will be placed in order. Our tomorrows will bear the mark of today through cause and effect, just as each new block can only be created with the last block. We understand that we cannot change the past. In blockchain, we say that each block is immutable. It cannot be erased. In history, nearly everything in the past has led to this present moment, the current block, the state of the world as it is today. The circumstances we find ourselves in is like the state of the current block. And finally, we know that time waits for no man. None of us can turn back the clock or even slow it down. A public blockchain is administered just as equitably. Nobody is treated differently. This is known as permissionlessness. What is a blockchain? It's like history. Okay, to understand the implications and possibilities of Web3, I'm going to restate the same idea in a couple of different ways. First, one thing you have probably noticed about history and time is that there is only one present, and as such, the present moment is precious. Should blockchains become our companions through time, they will share in each precious moment. Finally, now if that last block was valuable, you better believe the next block is also. The reason for encoding information in a blockchain is because that information is valuable. It is worth recording and preserving. What is a blockchain? A chain of valuable moments linked both past and present. Now that you have an idea of what a blockchain is, it's no wonder one of the first applications on a blockchain was about money. Money is generally the first thing you think of that has value. As we broaden our understanding of value for the user, the possibilities of Web3 begin to take shape. A blockchain is just information on a computer, right? How can it share so many properties with history? Anders Brownworth, a cryptocurrency researcher, has created an excellent online demo for understanding blockchains. Here you will find one of the core cryptographic functions used in many blockchains, the SHA-256 hash function. Then we will see how this gives the blockchain history-like properties. First and foremost, the hash function. A hash function simply takes input and produces an output hash. This hash is the empty hash because, as you can see, the input is empty. The first thing to note is the length of the output, 64 characters, even for the empty input. Now let's try something that's not empty. Let's try a capital A. Again, note that the hash output has changed. It is also 64 characters. This hash function has a fixed output size. No matter the input size, the output will always be 64 characters long. Now let's try a lowercase a. Output has changed, and even though it is slightly different than the previous input, the output is significantly different. In cryptography, this property is called the avalanche effect. Small input changes have large output changes. Now, you may be wondering if all of this is just random. It is not. It is pseudo-random. The uppercase a output hash is always the same, just as the lowercase a, and the empty hash. A function with one distinct output for one distinct input is called a deterministic function. Here are a few more interesting inputs and their hashes. Now imagine only being given the output hash. How hard would it be to find the input string? Well, I will give you a clue. It's basically impossible. This is known as a one-way function. It's easy to go one way, input to output, but nearly impossible to go the other way, output to input. And finally, while it is theoretically possible to get the same output for different inputs, it is very hard to find. This is known as collision resistance. Effectively, the outputs are unique per input. We will call this uniqueness. Here's a summary of the SHA-256 hash function properties. Fixed output size. The output is easily represented as 64 hex string characters. Avalanche effect. Even the smallest input tweaks will drastically change the output. Deterministic. Given the input, it's trivial to compute the same output every time. One-way function. Easy to compute, but nearly impossible to reverse engineer the input from the output. Collision resistant. Each output is unlikely to be like any other, creating a uniqueness for the output. Now let's look at a blockchain and see the effects of these properties. We will circle back on what all this data means, but for now, notice that each block has a set of data as the SHA-256 input and the corresponding output hash. This hash is a unique fingerprint that represents all of the input data on that block. If I try to change any of the data, the hash changes. And as you can see, things start to break. This is because each new block has the previous hash included as input. And any changes to the past will invalidate the blockchain. Just like history, we cannot change the past. It is immutable. Just like history, we have cause and effect through time. Importing just 64 characters, each new block is linked to all of the past. I hope seeing this quick blockchain visualization has helped solidify some of the nuts and bolts of a basic blockchain. You have a good idea of what a blockchain is, but what is a blockchain good for? It's time to bridge from the abstract to the concrete. Abstractly speaking, a blockchain provides a mechanism to durably capture value in an ordered log of events. I use the word durable to try and capture the real and present properties we get from the blockchain's immutable and temporal qualities. And I say capture value, describing data itself as valuable, but also the very act of curating or collecting the data also has value. Deciding how to add that data, how to incorporate it with the rest. This is capturing value. Now, let's make this concrete with a non-blockchain example. Just think about the lumber industry. Let's loosely think how value flows through the lumber industry's supply chain. Lumber is obviously the source of the value. To unlock this value, a logger must harvest the lumber and prepare it for transport. Next, a truck driver will transport the lumber to a sawmill, where a sawmill worker will cut the lumber to size and dry the building materials. Each of these things are valuable steps in the process. Each step adds value to the entire system. Once the building materials are fully shaped and stored in the warehouse, an inspector will grade the lumber, and then the sales reps can distribute the building materials to the retailers, where the customers will give value for value, money for building materials. Okay, think about this system and how value is transformed at each step of the way. Think about the resources and processes and roles that each contribute value to the system. Building in Web3 is about understanding the flow of value within a system and between systems. For Bitcoin, what does this look like? We have account holders, node operators. We have the Bitcoin nodes. The node operators maintain the nodes which perform the mining process, which validates account holder transactions and generates Bitcoin for the miners. For gaming, you have gamers, NFT artists, storytellers, game server operators, in-game resources such as gold, weapons, armor, or the characters themselves. Even the servers running the game. Processes might look like level grinding, quests, battles, whatever it may be. A user may also choose to play multiple roles in the ecosystem. The permissionlessness is an open door to all users willing and able to provide value to an ecosystem. The graph is a real-world example where you can clearly see that the creators of the graph understand the ecosystem in which they are building, which is to curate data from blockchain databases and make it accessible to application UIs. Here you can see some of the roles and processes that a user may choose to add value to this ecosystem. You may be a customer in this ecosystem, perhaps paying for the search service. If you are a developer, you can create your own applications on the graph. Or you can play a more supportive role by being an indexer, delegator, or curator, likely being compensated for your participation in the ecosystem. I hope each of these examples provided you a more concrete use case for blockchains. The Web3 economy is ripe for innovation. I have not seen this much excitement and innovation since the birth of the internet. And I would love to hear the ways in which you would like to innovate. Feel free to reach out on X or LinkedIn and be sure to mention you took this course. How are blockchains shared among peers? Because blockchains are dealing with the flow of value through systems, we might ask the question, who is actually interested in this value represented in the blockchain transactions? The answers may range from one individual to everyone on the planet. But perhaps more frequently, it will be some group of people that participate in or get value from any given ecosystem. The answer to the question is important because everyone interested in a given ecosystem will want to ensure that nobody is cheating the system. This is where we reach the important topic of consensus. Because the number of people and nature of relationships vary so widely in these ecosystems, consensus is one of the areas of innovation in the Web3 ecosystem. There are many consensus mechanisms. Some protocols are emerging to handle consensus in small, more personal blockchains, particularly in the self-sovereign identity space. Also, companies have decided that they want their own private blockchains, thus isolating the consensus. Some newer blockchains have embraced the natural structure of these groups and handle consensus on many different levels. The first blockchains, however, were built to address records of universal interest. Regardless of the size and scope of a blockchain, some way of achieving consensus is required. We will discuss the two most common consensus mechanisms in use today, proof of stake and proof of work. A consensus mechanism is a technique for getting everyone to agree on the state of the system, or the next block of transactions. It is also a form of validation that every transaction is following all the rules and nobody is cheating. One mechanism for getting everyone to agree is to centralize the decision-making power into one trusted authority. The central authority agrees, for a price, to personally make sure that nobody is cheating and to tell everyone the next state. Everyone agrees that whatever the central authority says is the next state. This will certainly achieve the goal of getting everyone to agree, but you might see a few problems with this consensus mechanism. Number one, you might want to check that they really made sure nobody was cheating, especially cheating for themselves. What you want is verifiability, which requires transparency. Number two, you have a single point of failure. The system could come to a halt if they disappeared for any reason. All right, let's try to fix these issues by selecting a node at random and requiring them to be fully transparent to allow us to verify their work. They have the responsibility of determining the next set of transactions and sharing that with everyone. Everyone will agree only if a supermajority can verify for themselves that nobody cheated. Okay, this can work, but what if the node selected does not validate for some reason, like maybe malicious, maybe not, or worse, they are malicious and end up just wasting everyone's time by purposely sending out invalid transactions that will just be rejected. What we need is to make it harder to be selected as the decision maker so that it is not worth the time or effort for any malicious actor to try and participate. The solution to this problem is where we get our two most popular consensus mechanisms, proof of stake and proof of work. In proof of stake, any node that wants to be selected must own a good amount of the cryptocurrency. That can be very difficult. Secondarily, a disincentive. The node must put their cryptocurrency at stake by agreeing to be penalized if they do a bad job, in which case they will be slashed, meaning lose some of the cryptocurrency. Every node that meets this criteria becomes part of a validator pool. One of them will be randomly selected to be the decision maker. The other validators in the pool will verify the work of the selected node. A supermajority must agree. Consensus achieved. The proof of work mechanism solves this problem of selecting a decision maker not through randomization, but by chance. Any node that wants to be selected must solve a very difficult puzzle, with all the transactions in a block being the puzzle pieces. It will take a lot of time and energy because the only way to solve the puzzle is to guess the missing piece called a nonce. The act of trying to solve this puzzle is called mining. The first node to solve the puzzle broadcasts its solution to the other nodes. They each validate the solution and add the solution as the next block in their chain. If the nodes find there are multiple valid chains, the longest one wins. Consensus achieved. I will admit it seems a little arbitrary to introduce solving a puzzle in the middle of this process, but it was literally just to make it hard to be selected as the decision maker. It's just chance. Solving a puzzle may be a little arbitrary, but it is also very clever. Are you ready to use a blockchain? Let's find out. blockchains require you to provide value to receive value. This is seemingly very different from how the internet works today. People think you can do almost anything for free. You can get a free email address, a free social media account. You can even search the internet for free. You might be thinking, hey, I like that about the internet. Isn't that a good thing? I like free things. The sad reality is that it's not actually free. You may have heard, if you're not paying for the product, you are the product. You are getting value through these services, but you do not realize that you are also giving value. You are giving away all of your data. You are even giving them your identity. Anytime you visit a new website that wants you to create an account, the method you choose to log in, that service, they truly own your identity. Web3 will facilitate a more conscientious exchange of value. All of this is to say that if you want to interact with a blockchain, you need to be prepared to exchange value. Often that means you are going to pay for the interaction. How is making the exchange of value more conscientious a good thing? Let me put it this way. If it cost money to send email, do you think you would have any spam? If it cost money to post a message online, do you think there would be much trolling? If it cost money to scroll through your social media feed, do you think you would spend less time doing so? Do you think you would be more intentional about how you consume social media? Yes, this could be a good thing. At the very least, we have the potential to remediate some of the most toxic areas of the internet. And remember, this exchange of value goes both ways. If someone is going to get paid for you to watch an ad, shouldn't it be you? Would you mind opening spam email if you were paid to do so? Would you spend more time crafting meaningful social media messages if you got paid for the number of quality impressions and interactions? Interacting with blockchains will require a bit of a paradigm shift, but I think being more conscientious of the exchange of value will bring more substance and meaning to the internet. Okay, how do I interact with a blockchain? You have to give it some instructions. You need to build a transaction and send it over the internet to one of the nodes on the blockchain. Because we are dealing with real value here, we should send messages in a secure manner. For this, we are going to need a little bit of cryptography. Public-private key cryptography. What is a public-private key pair? Imagine you have a key. Like any typical key, it has the capacity to do two important things, namely lock and unlock. What if we could magically split the key in half such that one half can only lock and the other half can only unlock? Anything the magic locking key touches will be magically locked and can only be unlocked with the corresponding unlock key. This is a little bit like public-private key cryptography. Cryptographers have been playing with these keys for a while now and have found many awesome use cases. If I lock a message with my private key, a key that nobody else has because I have kept it private, and I send that locked message to the blockchain, if the blockchain can unlock it with my public key, then it knows for a fact that it was locked with my locking private key. It is guaranteed that the transaction originated with me, since I'm the only one with the private key. In cryptography, this is known as a digital signature. Locking it with my key is like signing a document with an unforgeable signature. Signing transactions is a bit tricky on your own. That's why we have crypto wallets. The first thing to know about a crypto wallet is that they are not wallets. Not in the traditional sense. Your coins, tokens, or NFTs are not inside the wallet. Your crypto exists on the blockchain as an entry in the ledger, right next to your public key address. So if your crypto is not in the wallet, then what is? Your private keys. A crypto wallet's primary function is to manage your keys. You can generate keys, keep your keys safe, and use your keys to digitally sign transactions. Online wallets allow you to submit those transactions to the blockchain. You can also think of a crypto wallet like a web browser. A web browser enables you to see what's online. A crypto wallet enables you to see what is on-chain. So, for example, you can check your balances and look at the transaction history. Crypto wallets are another area of great innovation. This makes sense if you think of them like on-chain browsers. You now know how to interact with a blockchain. Blockchains require you to provide value to receive value, and your crypto wallet will help you build those transactions. That's it for this module on the basics of blockchain. I really enjoyed sharing this with you. We are opening a new chapter in the technological landscape. I cannot wait to see what you do with it. Before smart contracts, there was Bitcoin, blockchain's first major success. The creator, Satoshi Nakamoto, set out to create a purely peer-to-peer version of electronic cash that would allow online payments to be sent directly from one party to another without going through a financial institution. It was intended to be a global financial instrument, nothing more, and Satoshi wanted to keep it that way. Many developers could see great potential with just a few small changes to the Bitcoin code. But the informal and decentralized nature of Bitcoin prevented major changes. The developers, miners, and node operators would all have to agree to the change. Other perceived limitations had to do with the Bitcoin scripting language. It was too narrow and focused on one solution. Because the attempts to change Bitcoin met with such difficulty, many of the developers decided to either create forks of Bitcoin or create a new kind of cryptocurrency. Vitalik Buterin was one of these. He and many other Bitcoin developers left the Bitcoin community to co-found Ethereum. Bitcoin's perceived limitation inspired him to build a world computer of decentralized applications through the means of a general-purpose programming language he called smart contracts. What is a smart contract? The term smart contract comes from Nick Szabo back in 1994. He states that a smart contract is a computerized transaction protocol that executes the terms of a contract. Computerized meaning it will execute autonomously, no humans involved, no human error, safe, secure. Transaction meaning you give something and you will get something in return. Contract terms meaning the expectations are known up front. If you complete the terms, you know what the results will be, guaranteed. To help give a more concrete example, Mr. Szabo later described a vending machine as a primitive ancestor of smart contracts. While that may be true, I still find it the best way to introduce smart contracts. This little vending machine will help us gain insights into smart contracts. I see 4 valuable perspectives that will each explain some of the general use cases and strategic applications of smart contracts. First, the customer perspective, the perspective most of us are familiar with. Then, the owner perspective. The owner has special access and responsibilities with the machine. The internal perspective, understanding the dependencies that make the machine work. And finally, the external perspective. As people find new ways to adapt the machine to different environments, new ecosystems may form a dependence on the machine. When a potential customer arrives, nobody is there to service them but the automated system. If needed, the user interface will help explain the terms of the contract, but it is fairly well known and easy for a customer to comprehend. You put the money in, select the item you want. If you put in the correct amount, it will dispense the item. If you did not use the correct amount, it will wait until you do. Otherwise, you can cancel the transaction and you will receive your money back. As long as there were no mechanical errors, the vending machine will work every time. On the blockchain, the outcomes of smart contracts are guaranteed. The immutable code will run as written every time. The vending machine analogy is perfect because most machines are publicly available, and smart contracts are also publicly available, or permissionless. You don't need permission to use it, you just walk up to the machine and use it. From the owner's perspective, the location is important, not just for foot traffic, but in the case of a smart contract, the location or address is immutable, permanent. Even though we have immutable code and immutable addresses, the machine's state or storage is mutable. In the vending machine analogy, it's similar to the inventory. Inventory is mutable. It changes as customers buy, and it changes after being restocked. The owner is the only one that can restock the machine because they have the key. Smart contracts can have owners. It's not necessary, but it is possible. This is done in the smart contract logic by requiring something to be true in order to proceed. In this case, the smart contract can store the owner's wallet address and restrict certain transactions if they're not from the owner, thus allowing the owner to have some reasonable controls. Trusting the owner of a vending machine is usually not a problem, but trusting the owner of a smart contract who has privileged access can be problematic. That is why most smart contracts are open source and auditable. It can keep everyone safe from bad actors if you pay attention. When money's involved, people do crazy things. Vending machine owners can collect their money in two ways. One, manually collecting the cash in the system, and two, credit cards. Frequently in smart contract ecosystems, a treasury or liquidity pool is created to hold the value generated by that ecosystem. Generally, these funds are reinvested into the ecosystem, but we will leave that for another discussion. Having credit card readers requires that the vending machine have cellular coverage. This capability has been leveraged to create vending machine management systems. Data notifications for inventory, sales, reports, and alerts are now accessible. Smart contracts can also emit events. These events can trigger other smart contracts or front ends that are listening for the event, potentially building or augmenting many other systems. More on that in a moment. What if we want to change out the card reader for a better one? The card reader is internally dependent on a specific modem. Think of the modem as another smart contract. Changing the card reader would first mean changing the modem. Is changing an internal component even possible inside smart contracts? A vending machine enables the replacement of components via a control board called a multi-drop bus, or MDB board. The drops on the bus are for dropping in various kinds of devices: the modem, the bill collector, the coin receiver, the dispensing mechanism. Each drop location on the MDB board is an interface, which is basically another way of saying contract. To swap out a component, you simply swap out the interface's connection. It's a similar process for smart contracts. The code is immutable. The addresses are immutable, but the storage of a smart contract is mutable. By storing the address of a smart contract with the right interface, we're able to swap out the address at any time to point to a new smart contract with the same interface. Now let's think for a brief moment on how vending machines have added value to external systems. How have people and organizations decided to use vending machines to augment their environment? One simple way that does not require much effort is to provide common items that are commonly lost or forgotten. Hotels and motels can sell floss, toothbrushes, or other toiletries. I have seen socks being sold in bowling alleys, underclothing at swimming pools. Smart contracts can be integrated with minimal changes to an existing environment. Sometimes it's as simple as downloading an app to start reaping the benefits of blockchain. If you're ready to put in more effort, you can integrate well-designed, disparate smart contracts to provide new and innovative solutions. For example, what if vending machines could provide loans and background checks? What if they could vend cars? Getting a car complete with a loan would be fast and painless. Extending cellular coverage to vending machines enabled a revolution in vending management systems. Before, these systems were limited, manually collecting the data. Now they have real-time access to all the data they need. Companies can likewise have access to all the data on the blockchain by running a full node. While querying the data from the node is free, you will have to build teams dedicated to managing the node and processing the data for your applications. Smart contracts will affect all aspects of our lives, similar to the internet today. As individuals, we are all producers and consumers. We all contribute to society in meaningful ways. We also partake or bask in the talents of others. As a community, we come together to create things we could not create on our own, things that will benefit our families, governments, and organizations. This is the landscape for Web3 and how smart contracts fit into that future. We can each add value in Web3 and be rewarded. We will use the Web3 dApps in our daily lives. Smart contract innovation and new kinds of infrastructure will continue to be built, and the entire world will be better for it. How might smart contracts change the world for the better? Open protocols empower people. They facilitate innovation and collaboration without barriers. Freedom, liberty. Smart contracts are just a form of open and decentralized protocols. The Ethereum Foundation puts it this way: Ethereum is a protocol for human coordination. How is it that people coordinate? Whenever there is a group of people, they need coordination. We group ourselves in families, neighborhoods, churches, organizations, businesses, municipalities, states, nations, humans. We are all humans, all of us, together on this planet. We have an opportunity to leverage a global human coordination protocol. It is up to us to reach for something better. Throughout history, governments and powerful businesses have dominated human coordination through their lawmakers and affluence, leaving very little power to the people. It is still very early, but innovations in these areas are very interesting because of their potential impact. New cities are being built from the ground up based on decentralized principles. Sovereign indigenous nations are opting for Web3. Experimental models of taxation are being developed. Cryptocurrencies backed by the community's own land. Decentralized approaches to law are being developed, and code is being adopted as law. Government treasuries can be opened for full transparency. Governance tokens can be used to vote on the use of the funds in the treasury. Decentralized autonomous organizations are being created to run businesses on-chain. The decentralization of government power and business affluence will of necessity elevate individuals to take back their identities and their data, allowing the individual the ability to monetize their data instead of big tech. While people talk of wanting privacy, what we really want is a guaranteed confidentiality. All of these innovations and many more are on their way. We may call them different names as things evolve, but big changes are coming to a community near you. That's it for this module. Let me know what smart contracts you think will change the world. Next up, we will learn about Ethereum itself and the ecosystem surrounding it. In many ways, blockchain and Web3 has reignited the original promise of the internet. The original promise of the internet was to empower individuals and communities through the free exchange of information with open and decentralized protocols. The idea was that you should get a server and manage it. You would have email because it was your server. You could have a website if you put it on your server. Any internet service you like. You could decide how you would use it. A digital form of freedom and ownership. The original idea was that your server was like a little plot of land in a new global digital city. Digital property, secured by your physical property. It was all yours and nobody could take it from you. They would physically have to go through you first. You know what it's like to own something. You also know that ownership implies responsibility. And unfortunately, at that time, that responsibility was too great. Most people did not have the technical ability to own and operate a server for themselves. It was easier to outsource the responsibility to someone else's server, in someone else's possession, in someone else's control. And thus began the effective contraction and eventual centralization of the internet. Now, large big tech companies own a vast majority of the internet. We gave up our ownership and digital property rights. They own the servers and have cleverly asked us to give them our identity and our data. Fortunately, we are being given a second chance. Blockchain was miraculously invented in 1991 by Scott Stornetta, who inspired Satoshi Nakamoto, who inspired Vitalik Buterin, and kicked off a reignition of decentralization and open protocols, and has given birth to the next generation of the internet, where ownership is a prerequisite. We must accept that ownership and the accompanying responsibility this time, and we can do it simply by securing our private keys. Now, we are well equipped to fix the problems we created with Web 2, given that we all just happen to have supercomputers in our pockets. Everyone is equipped to take some responsibility for the ownership of our identity and data. It's a well-known fact that freedom is not free. I appreciate that Web3 asks people to be responsible. In a way, I think that being responsible is the minimum sacrifice we can make for freedom. Even better is playing an active role in the community. Not only will you secure freedom for you and everyone, but you will maximize your economic potential. Everyone will find some way to participate in the Web3 ecosystem, in part because that participation may have economic incentive. Perhaps it will be the equivalent of what we call a job today. You think I'm exaggerating? It's possible. Nobody knows the future. I invite you on a tour of the Ethereum ecosystem, where you will discover what is possible today, and you can decide for yourself what the future might hold. Here, we will discuss more about Ethereum itself, what it is, and how it's governed. This area represents the technologies that surround and enhance Ethereum itself. This is what I call the avatar layer. Not an industry standard term by any means. I'm only trying to emphasize the importance of this layer, because I feel it is so misunderstood by people entering the Web3 ecosystem for the first time. The avatar layer is about owning your identity and data. Some people call this your digital twin. I like to think of it as your avatar, because, like the movie, you control the avatar. And right now, big tech owns your digital twin. The avatar layer is about the role of wallets in the Web3 ecosystem. The final stop on the tour is where we will discuss dApps, or decentralized applications. We will begin our tour in the same place that a newcomer would, the avatar layer, and with a great analogy that will serve as an orientation to the ecosystem: Minecraft. If a group of friends want to play Minecraft on a private server, usually one of them will be motivated enough to build a Minecraft server on the internet. This friend owns and operates the server. Given the IP address, now everyone can load the Minecraft client and join the private server. Note that the communications protocol is Minecraftese, the language that is shared between the Minecraft client and the Minecraft server. At some point, everyone is asked to create a Minecraft user, so the game will know who is playing on what client. The client will store a little profile information and what worlds it has joined, but the server will have most of the information. If the data is lost, the whole game goes down with it. One of the burdens of owning a server. Because Minecraft is so extensible, people have created a web server plugin so that the owner of the node can manage the node with a web browser. Note that the communication protocol is the standard HTTP web protocol used every day by everyone using a web browser. I have even seen a plugin to enable the Minecraft server itself to make HTTP requests and allow the Minecraft clients to browse the web while in the Minecraft world. This setup has many similarities to the Ethereum ecosystem. The Minecraft server is an Ethereum node. The owner of the Minecraft server is the node operator. The Minecraft client is a crypto wallet. Minecraftese we will just call the client protocol for this example. If each of these servers are Ethereum nodes, we will call this server-to-server communication the Ethereum protocol for simplicity. Because the Ethereum nodes share copies of the data, the node operator does not have the added stress of accidentally destroying people's data if there are problems with the server. Creating the Minecraft user is like creating your keys. with one major difference. You actually own the character and all the items and equipment the character has. You own them as in it's your property. If you want to give away items or equipment, you can. If you want to sell your character to someone, you can. You can go to any Minecraft world and interact. You could take things from one Minecraft world to another. You could feasibly enter a metaverse with your Minecraft user. It almost makes your character seem real, doesn't it? Like an extension of yourself, almost like, would you say, an avatar? It's real enough that if you are not careful, someone can take it from you. That's right, if someone had access to your character, they could take it. This is the same as your private key. Your keys enable a very real kind of ownership. If someone takes your keys, they have the power. Securing our keys must be our responsibility. The last major difference to note. Recall that in the Minecraft ecosystem, the server owner had a web interface enabled by a plugin. 2 interfaces, 2 protocols. Notice here that the protocols are coupled at the server level. In the Ethereum ecosystem, the coupling will be at the client level. And the web server will be separated out and called a dApp. There are many ways of architecting a dApp, but this is a very common way. Because of this client-level coupling, we often see wallets and web browsers used together. On desktop computers, the wallet is embedded in the browser as an extension. On a mobile device, it's the other way around. A web browser is embedded in a wallet app. MetaMask is a great example of this. This concludes the avatar layer and Ethereum orientation portion of the tour. The keys in your crypto wallet are just as important as the keys to your home. They are the keys to your digital property. Don't let them go. Ethereum is at the heart of the ecosystem. And I think the best way to describe Ethereum is to compare it with Bitcoin. It's a little easier to understand. Bitcoin was created with a very specific purpose. It was built to do one thing well. It is able to remove the need for intermediaries like banks by replacing them with a consensus network. We often refer to this as the Bitcoin network, which is separate from Bitcoin, the asset. To describe the purpose of Bitcoin in one word, I would say money. The purpose of Ethereum was to be the world's computer, a shared global resource. To prevent misuse of this resource, those who want to use it must pay Ether, proportionate to the computation needed. Bitcoin uses the same word to describe the network and the asset. The same is frequently true of Ethereum, but technically Ethereum refers to the network and Ether refers to the asset. To describe the purpose of Ethereum in one word, I would say compute. The application for Bitcoin is obvious. Allow users to store value and securely transfer value, period. But for Ethereum, a single application is not enough. A computer is useless without its many applications. The Ethereum virtual machine, or EVM, is the runtime that processes the smart contract transactions. This is what makes Ethereum Turing complete. It is the runtime for any smart contract application. Because Ether is needed to run an application, the applications are not only providing value, but they are also efficiently and effectively doing so, to avoid wasting any Ether. The data needed for the Bitcoin application is effectively just a ledger. But for Ethereum, each application would have to decide what to store and how it should be modeled. It's tough to beat Bitcoin's transparency. Owing to the fact that it has one specific application and one data model, it's easy to see exactly what it's doing. Every account balance and transfer is fully transparent. Ethereum's Ether has similar transparency to Bitcoin, but the dApps and their data models are a little more obscured. You must read the open source smart contract to gain full transparency for any given dApp. The last distinction between Bitcoin and Ethereum I would like to make is a circumstantial one. Because Bitcoin's creator is unknown, the Bitcoin ecosystem is very stable. Any changes are highly collaborative. Ethereum is also very collaborative. However, since Vitalik Buterin is credited as the creator of Ethereum, his opinion has great influence on the entire ecosystem, which begs the question, who controls or governs Ethereum? One answer to this question could be no one, because indeed no one person controls Ethereum. There is no CEO, there's no one calling the shots. Even Vitalik Buterin is very unassuming. The most correct answer to this question is the Ethereum community. One great thing about the Ethereum community and many other open source communities is that they are very decentralized. They share the same ethos as the blockchain: open, decentralized, consensus. The Ethereum community is made up of developers, validators, and various organizations with a vested interest in Ethereum's success. Most open source communities have open discussion, and anyone can make a proposal for the community to adopt. The developers may be the biggest force for change. After all, they are the ones making the changes. The developers continue to meet several times a week. They post their meetings on YouTube. All proposals for Ethereum can be read here. The Ethereum standards come in two primary forms: EIPs and ERCs. EIPs, or Ethereum Improvement Proposals, are global changes that affect most or all of Ethereum implementations. ERCs, or Ethereum Request for Comment, are smart contract standards, so the community has standard guidelines to operate with. EIPs are often implemented in the Ethereum protocol, while ERCs are implemented at the application level. Broad consensus is required for EIPs because it must be adopted by all nodes. ERCs need general adoption from the participants in the portion of the ecosystem the standards will affect. Not everyone will need to adopt the standards all at once. They can be adopted at will. Repositories for both standards are maintained on GitHub. What are some examples of EIPs? Remember, these are big changes that everyone must adopt. Things like EIP 1559, which made Ether deflationary at times. Another big one was EIP 3675, which deprecated Ethereum's proof of work and became proof of stake. What are some ERC examples? ERCs are application standards. With smart contracts, it became possible for people to make their own cryptocurrencies. Everyone who wanted to make a cryptocurrency also needed the ability to manage and trade them. ERC20 became the token standard for building assets with the rights and utility beyond the underlying cryptocurrency such as Ether. Other popular standards you may have heard of are NFTs, or non-fungible tokens, ERC 721. This made it possible to create unique assets on-chain like art instead of fungible assets like tokens. Another popular standard is the Ethereum Naming Service, or ENS, where people can register names on the Ethereum network, like registering a domain on the internet. This became a standard with ERC 137. That is the essence of what Ethereum is and how it is governed. I hope you took the time to pause the video and learn more about what may have interested you. If not, now's a good time. Ethereum's popularity and utility, along with its shortcomings, inspired others to create new blockchains. Many of them adopted Ethereum's virtual machine and enabled smart contracts to migrate off of Ethereum. Ethereum's success had led to higher gas fees. Some innovations seemed impossible because blockchains could not access data outside of the blockchain, or because the dataset was just too large to store and manage on-chain. The solutions to these problems are found in this area of the Ethereum ecosystem, directly enhancing Ethereum's capabilities not by changing Ethereum, but by adding infrastructure around it. Gas fees go up as more and more people use Ethereum. The competition for compute drives the prices higher and higher. This is a scaling problem. How do we get more computation power? There are many scaling solutions, such as sidechains, state channels, validiums. They all have their benefits and should be considered for each use case. But the current scaling solutions that are favored by the community are Layer 2 scaling solutions. As the name implies, a Layer 2 will have a dependence on a Layer 1. L2s derive security, data availability, and censorship resistance from the underlying L1. A simple example of this is called a payment channel. Imagine opening a tab at a bar. The L1 is responsible for monetary transactions. The L2 is responsible for the orders. Instead of paying the register for every drink, the bartender will keep a record of the orders. At the end of your time at the bar, you settle the tab by paying for all the drinks in effectively 2 transactions, opening the tab and closing the tab. Ethereum can do much more than payments, but you can see how this simple example reduces the transactions on the main chain. The most popular L2 solution is known as a rollup. Again, an analogy, not to get too technical. Imagine you own a really busy restaurant. That might sound like a good problem to have, but your restaurant was intended to serve everyone. You have an open door policy. Nobody can be turned down. Prices are high because people can choose to pay more for service. Everyone is complaining about the prices. After several discussions, a solution is reached. Franchising. You will open up new shops to handle all the load. Someone brought up the concern that one of these franchise owners might turn people away, or otherwise not follow the rules. So part of the solution was to have special accounting software at each location. They could not get paid for their orders unless they submit a batch of orders and pass an audit each time. They can audit each other and get paid if they find any fraud. Finally, if someone suspects they are not being treated fairly, they can submit a complaint back at headquarters. This is rollups in a nutshell. Each L2 rollup is basically another blockchain that submits batches of transactions to the main chain for settlement, drastically reducing the fees on those chains. You will hear about two kinds of rollups. Each has a different auditing technique. An optimistic rollup takes the optimistic trust but verify approach, and the ZK rollup uses zero-knowledge cryptography to just verifiably pass the audit. One question you might ask is, how are these blockchains sending messages to each other? Bridges enable blockchains to share tokens and data with each other. This is not only used in rollups, but a common technique for all blockchains. This will foster more innovation because people will have more choice and more competition in blockchains. One more note about wallets before we continue. Now that we have introduced multiple blockchains, I want to point out that a feature in your crypto wallet is network switching. In order to take advantage of the lower gas fees, you have to point your wallet to an L2 network. But just by switching networks does not move the assets. You will also need to bridge your assets over to the L2 so you can use them. There are three main ways that bridges transfer tokens and data. Lock and mint. The bridge contract takes control of the assets, locking them so nobody can access them. Then new assets are minted or created on the new chain. To send them back, the bridge contract will burn the tokens or make them inaccessible to everyone forever, and then release the original tokens. Burn and mint. The bridge will burn the original assets, and then new assets are minted on the new chain. And going back would be the same process, burn and mint. Atomic swaps. Here, the bridge acts as kind of an exchange for all the users. As users want to bridge their assets across chains, the bridge will just swap the assets of the users on chain, so everyone gets what they want. Okay, but what if you want something else, like the results of a sporting event? Blockchains are natively siloed to the data that is on chain. This is because blockchains must act deterministically. So writing a smart contract to behave according to real-world events, like the results of a sporting event or the weather, is challenging. In order for this to be done, somebody or something would need to write the information to the blockchain, and it would have to be done by a credible source. Oracles provide data to the blockchain in this manner, either by constantly writing to the blockchain, which could be expensive, or by responding to a request transaction, emitting an event for an off-chain system or process, and then write to the blockchain the results of that request. All right, that is an oracle. Now, what if there's just so much data? It would cost too much to write to the blockchain. Some applications work with very large datasets. Because storage has gas fees, it can be prohibitive on chain. For this reason, you will want to keep large datasets off-chain. You could choose a Web2 solution, but this course is about decentralized solutions. May I introduce decentralized storage, or D-storage. We have already discussed one form of decentralized storage, on the blockchain. The type of data stored here must be valuable and of a manageable size, because each transaction will spend gas to update the data. Any data stored on chain is guaranteed to always be there. Some data does not need to exist forever, but only for a certain period of time. For this kind of data, you can pay for a contract-based storage. The data can be of any size and will be persisted according to the contract. A very popular decentralized storage protocol is the Interplanetary File System, or IPFS. Anyone can create a node and store any amount of data for free, as long as they maintain the node. If you don't want to maintain a node and would still like to use IPFS, the contract-based storage providers usually provide an IPFS pinning service you can use. Those are the highlights of the auxiliary infrastructure surrounding and enhancing Ethereum itself. Now it's your turn to do some research. Read up on L2s and try to use one today. The last leg of our tour, the dApps. Every application has a form of storage, compute, and access. An application may have centralized data and compute, or decentralized data and compute. It may be permissioned, or permissionless. Or perhaps a little bit of both. dApps are a new kind of technology where blockchain technologies become accessible to the average user. Any application that uses decentralized or blockchain technology, I would call a dApp. For example, Farcaster, a social media dApp, has permissioned access by default with centralized compute and centralized storage, with the exception of one thing that is stored on chain, the ID. An ID that can be claimed to achieve permissionlessness. The fact that this uses decentralized technology at all means this qualifies as a dApp. Baby steps to Web3. Baby steps to Web3. Uniswap, on the other hand, is permissionless, with decentralized compute and decentralized storage. There are a few aspects of centralization just to get a return on their investment, but the ethos of the company and its solutions are very Web3. When you are learning about dApps, always think about how decentralized it is. One large genre of dApps must be discussed, that of NFTs. The 2020-2021 bull run saw a huge spike in interest for NFTs. The primary utility was digital art, mostly for social media profile pictures, but also for NBA pictures and digital trading cards. I remember NFTs being ridiculed as just being a JPEG. People did not understand that it is really about ownership, cryptographically verifiable ownership. Some people saw beyond the hype and began innovating. The arts branched out into musical NFTs. I recall an interesting project that issued NFTs as crypto bonds. My home state of Utah began issuing and verifying marriage licenses as NFTs. I could even buy an NFT that would give me popcorn for 5 years at the movie theater. That's the other thing that makes this not just a JPEG, utility. The NFT grants you certain privileges because you can prove that you are the owner. Another overlooked innovation was the concept of an NFT marketplace. Marketplaces are a big deal. Even when I travel, I love finding a little marketplace of street vendors. The marketplace not only brought people together to buy and sell their NFTs, but the smart contracts behind the marketplace ensured that the authors would be rewarded each time the NFT was sold. Respect. When you think about it, the metaverse, or another gaming platform, is nothing but another NFT marketplace. It's a place that brings people together with a common interest in a particular market, in-game assets, digital skins, clothes, land, buildings. I think quests from Dungeon Master types should also be an NFT, like an experience inside the metaverse game. All of these NFTs can only be seen and experienced from inside the game. A JPEG would be insufficient to describe the NFT asset. Yet another way that NFTs are more than just a JPEG. I know more innovation is coming for NFTs. I can see them as university degrees, as certificates of completion, as a credential or a license. All these things can be instantly verified on-chain. These innovations will affect our daily lives. I cannot wait until all of these NFTs are part of our self-sovereign identity. Speaking of our IDs, one problem with Web3 is the crazy hexadecimal numbers used to send and receive cryptocurrencies, your public key address. There are a couple of dApps meant to make referring to your public key easy, similar to how we use web addresses today to refer to an IP address. ENS and Unstoppable Domains. Check them out and pick a name for your wallet. That's it for this module. Ethereum and its ecosystem is a lot to take in. I hope some things piqued your interest and you are excited to go and learn more about Web3. Up next is learning the basics of the Solidity programming language. I've been programming for many years. I have seen many programming languages and contracted for many large corporations. When I turned my attention towards Solidity, I was amazed at what I found. Okay, what I wish someone told me about Solidity. Top 3 things. Number 3, contract first development. Just having an emphasis on the interfaces of your code. How long have we as an industry been trying to get people to write unit tests and think about the design of their components? Nobody is going to deploy a smart contract without 100% code coverage, because the name of the game is immutability. Changes are hard. We are going to get that thing tested, and interfaces well designed. Okay, number 2, an emphasis on event-driven architecture. Events are the best kind of coupling. The publisher declaratively states something has happened and has no care in the world for who is coupled to that event. Seeing events as a first-class citizen was very exciting to me. The fact that they can be listened to on and off chain is amazing. And number 1, no data layer. No data access objects. No object relational mappers. No tables. The absolute best part about this is that business people will not get confused by their dev teams talking to them about tables, because they don't exist. Nobody is going to change the name of a field in a database table and break the front end because they can't. It doesn't exist. The insane levels of coupling you need to pull something like that off just don't exist. The only consideration of data is, where is it located? My variable is either stored on chain or in memory. That's it. Because it's a global decentralized computer, it's as if it's never off. It's as if it's always running. No crash will wipe out your data. You don't need to restart any services. No IT team will accidentally pull the plug or change a setting. It will always be there, in the last state that you left it. No, I'm not saying we don't need databases anymore. I'm just excited that there exists a runtime environment where they're not needed. We will always need them for reports and other denormalized data needs, but there it is, number 1 in my book. We have a runtime so thin that persistence is automatic. The interfaces are clean. And events, the best kind of coupling, is a first-class citizen. That just makes me giddy. The 2 most supported smart contract languages for the EVM are Solidity and Viper. If you are familiar with Python, then you may enjoy Viper best. If you want to jump in immediately with a fully hosted IDE, then try Remix at remix.ethereum.org. Let's learn Solidity by example. We will ease our way in with a few simple examples. Then we will look at a few select examples from soliditylang.org for a little bit more realistic examples. To create a smart contract, we use the keyword contract followed by its name. Each contract can store data on chain. This one is storing an unsigned integer. We can define a contract's behavior with the function keyword. As you can see here, the set function will update the on-chain variable. We also call on-chain variables storage. Because this function is updating storage, when executed, it will have gas fees. This function is also public, so anyone willing to pay the gas can call the function and update the integer. This function is also public, however, it is marked with the view keyword. This means that the function is not updating storage and is therefore free to call. Overall, this contract lacks a clear purpose. Why is this integer so important it would run on the world's computer, allowing anyone to change it at any time? If you can think of a reason, I would love to hear in the comments. This contract also stores an unsigned integer as part of a mapping. A mapping associates or maps one value to another. An address is a special type in Solidity. It represents an Ethereum address. Each Ethereum wallet has an address, and each smart contract has an address after it's been deployed to the network. So the numbers mapping represents the favorite number for any address. If an owner of an address does not set a number, it will be the default value for a mapping, which is 0. Which is not a bad number actually, a rich history there. It might actually be their favorite, but I digress. Similar to the last set example, anyone can call this public function who is willing to pay the gas for updating storage with their favorite number. Solidity is aware of the caller's address via the message sender property. Message is a global context variable with information regarding the message that was prepared to call the smart contract. Because Ethereum addresses are public, anyone can call this function with any address for free to find the associated address favorite. Overall, this contract is more useful. I can think of several group games where this would come in handy just to make sure people are not cheating. The usefulness of a contract is not limited to people calling it directly, but may also be useful for other contracts. The Lucky Day smart contract needs a number associated with an address in order to inform the address owner if it's their lucky day. The algorithm does not care why there is a number associated with an address, just that there is a number associated with an address. In this way, the favorite number smart contract is part of a whole class of contracts that all give address numbers. We can call this class of contracts an address number provider. As long as the contract has a public getNumber function that returns an unsigned integer given an address, then it is a member of this class. How many ways are there to associate a number with an Ethereum address? You be creative. Let us know in the comments. For example, because the Lucky Day algorithm is public, you could just create your own address number provider to ensure that every day is your lucky day. The address for the address number provider is specified in the constructor. The person deploying the contract must specify an address number provider address. For now, we could just pass in the address of our favorite number contract. Constructor functions are only run once during deployment as the contract is being created. This function allows the replacement of the provider address. As written, anybody calling this function would select the address number provider for everyone using this contract. We could improve the contract by allowing each address owner to choose their own provider. The Lucky Day algorithm instantiates the provider to get the number. By modding the number, it is brought into the range 0 to 6. We do the same for another global context variable called block timestamp. The global block variable has context information regarding the current block in the blockchain. If the two numbers are equal, it's your lucky day. Our next example will come from soliditylang.org. The ballot contract is about voting with delegation, meaning a voter can give someone else their right to vote. Here we have an example of a struct. This is defining a voter type with properties each voter needs to participate and to prevent voter fraud. The voters will be voting on proposals. This type will track the count for each proposal. Notice that the name field is not a string. Sometimes a bytes32 is used to avoid bugs and improve efficiency, thereby reducing the gas fees. The Ethereum client library has utilities to help clients convert strings into bytes32. These are the storage variables for this contract. The chairperson is responsible for gathering the proposals and certifying the voters. Normally, they would also be responsible for counting the votes, but this smart contract will do that in a trustless way for everyone involved. The voters mapping represents all certified voters. Proposals is an array type to store the list of proposals. The chairperson must deploy the contract with the pre-selected proposals. Notice the memory keyword. This is called the data location of the variable, either storage or memory. Reference types such as strings, arrays, mappings, and structs could be referring to on-chain storage or referring to temporary data stored in memory. Here, the proposal names in memory are pushed into the proposal's storage variable. The message sender inside of a constructor is a little more significant. Not only are they the caller of the function, but in this case, they are the creator of the smart contract. This is the first example of an address playing a special role in a contract. Here, that is the role of chairperson. Only the chairperson can certify voters and give them the right to vote. The require is a global utility function. It requires that a certain statement be true, otherwise you cannot proceed and an error is returned. If anyone other than the chairperson calls give right to vote, then the message sender will not match the chairperson's address. You can see here a few other fraud prevention require statements. If all conditions are met, then the voter is given their right to vote. These three functions are using the external keyword. This prevents them from being accessed from within the smart contract itself. Why is this important? By limiting the possible places it could be called from, we are limiting the number of security concerns. We only want these functions to be called from individual wallet addresses that belong to the voters and chairperson. External functions still could be called from other smart contracts, but they will have no way of accessing any internal state. I'll leave the rest of this for you to look at. You can find the code on soliditylang.org in the Solidity by Example section here. I need to show you how easy the events are. In the blind auction example, an auction-ended event is defined using the event keyword. You can also specify the data needed to instantiate the event. Later, when the auction end is called, we can emit the event instantiated with the data it needs. It's that simple. Anyone listening for the event will be notified, and the events will remain in the blockchain logs forever. The final example we will take a look at is the micropayments example, again from soliditylang.org. I have broken it up into separate files so that we can see how imports work. This first contract encapsulates the idea of an owner. We are using the constructor message sender trick to store the owner of the contract. Notice the payable keyword. This adds transfer and send functions to the address for this micropayments example. The freezable contract imports the owned contract and inherits from it. This contract encapsulates the idea of a frozen account. This special function is tagged with the modifier keyword. This makes the function a decorator, meaning it can be easily added to any function. The underscore represents where the wrapped function code will go. For this example, receiver pays is a freezable contract, and the claim payment function is using the not frozen decorator. Anyone calling the claim payment will actually call the not frozen function, and the claim payment code will run at the underscore. Well, I think that's deep enough for today. I hope you feel comfortable with getting your feet wet and trying some Solidity. Here is the official documentation, and if you want some great tutorials, you can find them at ethereum.org. All this talk about immutable code and such might scare you away from development. Not to worry, there are development tools and frameworks that let you architect, build, and work out all the bugs. Let's start with what we are familiar with: a regular front-end application and a regular back-end application that the front-end uses. Regular development, regular builds, with regular tests, and regular deployments on regular infrastructure. How is the Ethereum stack different? Well, the Ethereum stack should include the Ethereum blockchain. Each node on the chain comes complete with the EVM and all the smart contracts ever deployed. Next, we add an Ethereum client library, either in the front end or in the back end. If it's added in the front end, it will likely be a JavaScript library. If it's added in the back end, it may be Python or a Java library. Either way, we have our Ethereum client component, able to connect to a node on the blockchain. The Ethereum client must have private keys to transact with the blockchain. Where the client resides, front end or back end, is also a question of custody. Will the end user have the keys, or will the organization? Regardless, as far as the Ethereum stack is concerned, it's all the same. This is the Ethereum stack. The EVM, running smart contracts on an Ethereum node, being accessed by an Ethereum client library, running in an application. To build on this stack, we need some special tools and frameworks. The Ethereum client library, such as Ethers.js and Web3.js, have an important role to play, bridging the gap between the application and the blockchain. The client library has the ability to query the node for information about accounts and other general information about the node itself, so that the application can display balances and other details. When the application needs to call a smart contract, the Ethereum client can sign the transaction and send it to the smart contract. After the transaction is processed, it can obtain a receipt, which describes the block information as well as its success or failure. If it failed, the application can notify the user. If the application wants to respond to an event on chain, the client will listen for that event and execute any handlers the application provided. The client is also integrated with global standards such as ENS, the Ethereum naming service. Any addresses registered on ENS can be displayed in the application with the user-friendly name. From a development perspective, the Ethereum client library is a perfect unit testing library when wrapped in a unit testing framework. It also houses many cryptographic and hash functions, as well as common type conversions needed when dealing with smart contracts. And probably the most important thing, from a development perspective, it can deploy the smart contracts to the network. In order to build for the Ethereum stack, we first need to find a blockchain we can use. The mainnet is out of the question because that would cost real ether. We could build our own Ethereum node, but then we would lose out on better developer tooling. We could use the testnet, but that is more of a staging environment. Fortunately, many of the Ethereum development frameworks have a local blockchain packed with developer-friendly features, like seeding ether to test accounts, instantly producing blocks in the order received, and enhanced debugging and logging. Next, we need the ability to compile and deploy it to the local blockchain. Many development frameworks have configurations for the deployment, making it easy to choose which network to deploy to. Finally, in this immutable world of blockchain, we need to have the ability to test smart contracts and get that code coverage to 100%. These testing frameworks generally have an integration with an Ethereum client library, making setup easier. Some of the more popular Ethereum development frameworks are Foundry and Hardhat. At the time of recording, Truffle has already announced sunsetting and forming a partnership with Hardhat. You can find other frameworks listed on ethereum.org. Let's get Hardhat running from scratch, and then do some unit testing with Ethers integration. I'm using VS Code, and here is my node version and my npm version. We are going to make a directory for the demo and open up VS Code in this location. Start an npm project with all the defaults, and then install Hardhat as a dev dependency. We should get the Hardhat VS Code plugin. We can initialize a Hardhat development environment like so. I will choose all the defaults. The default project has this lock contract. It will lock any value you send to it at the time of creation, until the time specified, after which the owner can request a withdrawal. It also has a great unit test example, very thorough. When you compile the project, it builds all the artifacts it needs here. And this will run the unit tests. All passing. The test command actually compiles the contracts and spins up a local blockchain to test against. Once the tests are complete, the local blockchain is torn down. You can manually spin up a local blockchain for any other local testing you may want to do. This is where it's located. It's just another blockchain network, so you could go to your browser wallet and switch networks to the local blockchain. You can also see that Hardhat provided plenty of test ether across, it looks like, 20 addresses. To deploy the contract to this local blockchain, we can use Hardhat Ignition. This ignition file declaratively states how we want to deploy the contract. It specifies the date we want to unlock the funds and how much ether to lock up. We need to tell Ignition where the configuration file is. And also specify that we want it to deploy to the local blockchain. Props to the Hardhat team for making this so easy to start building on Ethereum. Now let's dive into the test features. Let's start with the favorite number smart contract. To test this, we need some accounts so that they can choose their favorite number. The Hardhat Runtime Environment, or HRE, has made the Ether's Ethereum client library easily available without any additional configuration. Remember those 20 test accounts on the node? We can just pull them in with the Ether's getSigners function. Let's pull in just 4 of them. All right, next we will ask Ethers to deploy the favorite numbers contract. Okay, it's time to start choosing favorite numbers. We can specify which account is calling the contract with the connect property, then call the set number. Now we can call the getNumber function to see if it remembers the right favorite numbers. We can access the account address with the address property. Let's verify that if someone has not set a favorite, that they will get the mapping's default value of 0. All right, this test looks complete. Let's run it and see the results. Perfect. Okay, now let's see a more advanced test where we need to manipulate the time on the blockchain. A lucky day test. Okay, similar to last time, we will use Ethers to pull in some users. This time, we have 2 contracts we need to deploy. Favorite number is deployed first. It will act as the address number provider for the lucky day contract. The target field is the address of the contract. This is needed to deploy the lucky day contract because it's part of its constructor. I'm going to save off the favorite numbers because we will reuse them to get the correct results in the lucky day contract. Now, similar to the last test, we will set the favorite numbers. If I ask the contract now if it's our lucky day, we will get mixed results. Sometimes it will fail on line 29 and sometimes line 30. This is because the blockchain's time is different every time we run the tests. To fix this, we need to manipulate the block timestamp. We need to import the time helper from this Hardhat network helpers library. This little helper function I created will get the current time and increase the time to a point where the person's favorite number will generate lucky day results. We can just add this before each call and voila. All green. Again, props to the Hardhat team for making such great tools. That's it for this module. Up next is the final module in the course, an introduction to decentralized finance. One of the largest sectors in the Web3 ecosystem is decentralized finance, or DeFi. Satoshi Nakamoto wanted to get rid of financial institutions as intermediaries for the exchange of cash. If you think that Bitcoin is a type of cash, then mission accomplished. If you are a financial institution or work for one, you might see this as some potential competition. And it does not take a rocket scientist to see that Bitcoin does it faster, cheaper, with effortless global reach, any hour of the night or day, and in a completely egalitarian and equitable way. How are financial institutions supposed to compete with that? They might say, we're safe, it's not really a competition, it's just Bitcoin. We manage fiat currencies from nation states. Nothing to worry about, right? Well, there's this thing. It's called a stablecoin. It's a cryptocurrency that is the same value as the fiat currency it represents, dollar for dollar, pound for pound, yen for yen. And it can be transferred faster, cheaper, with effortless global reach, any hour of the day or night, in a reasonably egalitarian and equitable way. So, not really safe from that. Okay, but money transfers are just one financial service. There are many other financial services. Let's think. What other services do financial institutions provide? Well, they provide credit and lending services. Most of us have experience with auto loans and home mortgages, regular old credit cards, perhaps personal lines of credit, a little debt consolidation. They provide investment opportunities in money markets and brokerage accounts, during business hours. And they provide insurance products, mitigate some of that risk. Well, for all those traditional financial institutions out there, I have some bad news. You have a competitor for all of these services I just mentioned. Decentralized finance, or DeFi. We already have DeFi applications providing similar services today. They cannot replace traditional financial institutions right now, but with the amount of innovation and cross-pollination from other Web3 sectors, it looks like a possibility. In short, the financial industry is about to be disrupted. Big time. And it's about time. Most of these financial institutions are still running tech from the 1970s. Some of you might be wondering, replacing traditional finance? How is a service being provided without a provider? Right? It's like I'm saying you get a loan without a bank, or you get insurance without an insurance company. Who is providing the service? Well, like most things in Web3, the answer is anyone. Anyone can provide the service if you have the means and the desire to do so. Do you realize what this means? Where a bank would earn the interest on someone's loan, now you can earn the interest. Where a brokerage would earn fees on facilitating somebody's trade, now you can earn the fees. Where insurance companies would earn premiums providing coverage for your neighbor, now you can earn the premiums. In other words, the people provide people with financial services through decentralized open protocols. DeFi is finance of the people, by the people, for the people. Now, to those TradFi viewers out there wondering what to do about all this, just FYI, these protocols don't write themselves. There is a new kind of financial institution in Web3. These companies are building the DeFi protocols, as well as the platforms for the users to engage with these protocols. Even though people can earn fees for supporting these protocols by providing liquidity, these new kinds of financial institutions also get a cut of the action. What to do about all this? Get in the action. If you can't beat them, join them. Not everything can be put on chain. TradFi will likely continue providing advisory and consulting services. In my opinion, however, banks need to reimagine themselves as major players in Web3. Maybe they can provide reporting services from on-chain data. Maybe they can help build smart contracts to replace or comply with regulations. Maybe they can build services for businesses to manage their cash flow effectively on-chain. So, it's time for everyone to roll up their sleeves and think outside the box. At the very least, you can build your own platform and use the same protocols. There's plenty of room for innovation and growth in decentralized finance. Looks like we've reached the end of this module as well as this course. I hope you've enjoyed it as much as I enjoyed making it. The adoption of Web3 technologies is my highest professional priority. If you think so too, then please invite your friends to watch this course. Feedback is important to me, so please rate the course and leave a comment. Don't be a stranger. Bye now.